Still thinking about free body diagrams at one point? Let's look at a second example. Here is a weight hanging from a rope. The rope's connected to a wall, and in between there's a bar that the rope is draped over, and the bar is connected to the wall. And we know the weight weighs 100 pounds, and we know the angle of the bar and the rope. But good heavens, are the bar and the rope strong enough? How much force is in them? So first of all, let's just think about who is in tension and who is in compression. Well, it's clear that this weight is hanging from the rope, which means that rope has got to be in tension. And it also seems like because that rope is connected to the wall and kind of everything's pulling away from the wall, this upper section of the rope is probably in tension as well. And if this bar is holding up the weight in the rope and so forth, or the weight in the rope or pushing down on the bar, this bar is probably in compression. It's probably feeling pushed on. So now we want to get out our free body diagram analysis tool, very important, and forget about everything else that's going on, just that one joint. Focus in on that joint. By the way, this is going to be exactly the same method you'll do when you're analyzing a whole truss. You get your analysis tool here, your paper towel tube. You don't look at anything else except one joint. Forget about the rest of it. And you just work one step at a time. So here we are on this step. There's our joint that we're focusing on. Who cares how it's connected to the wall? Doesn't matter. We're thinking about the forces in the rope and the bar. And we're thinking that the rope hanging down is in tension, so that arrow is pulling away. We're thinking that the rope up above is in tension, so that arrow is pulling away. And we're thinking that this support bar must be in compression, so that arrow is pointing towards. Well, we know one magnitude. We know that the downward force is 100 pounds. So we can draw that arrow 100 things long. Now the others, we don't know their magnitudes, but we do know their angles. So we could draw, there's the upward arrow for that bar, and we could draw, there's the outward, the pulling away arrow for that rope. So there are our three things, and we could now measure how long they are. And now, oh yeah, and I wanted to say, sorry, let me go back here. This relates to the second problem that you're going to work on. I meant to say that. So here, same situation. You got a weight hanging down, much bigger weight, 5,000 pounds hanging down. It's causing a tension in this cable from A to B, and then those are causing a compression, a pushing on this bar from A to C. And your task is to figure out how big is the tension in AB and how big is the compression in AC. And I've put the answers at the bottom of this slide. These are the numbers you should come up with. You might be off by a little bit. That's okay. You want to be close, but if you're off a little, you're probably correct. So now, forget about the wall and you're looking at that. Now the first thing we need to think about is how do we draw those blasted arrows when they don't give us an angle. So here, for the cable, we have a slope that is over 12 and up 5. So we can draw in AutoCAD, we can go over 12, up 5, connect the dots, there's our slopey line. For the bar, looks like we can go over 12 and down 9 and connect the dots, and there's our slopey bar. Here's our free body diagram of that joint with tension pulling away and compression pushing towards. So we can draw one thing 5,000 units long. This bar in compression pushing towards, we don't know the length, but we could draw the angle. And this cable pulling away, we don't know the length, but we could draw the angle. So now, let's go over to AutoCAD and look at our example number 2 here, which is similar to our second homework problem. So here is our example number 2. We've got a 100-pound weight hanging down, a bar at a 40-degree angle off of vertical, and a cable at a 30-degree angle off of horizontal. One thing you need to watch out for is, are you going 40 degrees off of vertical? Make sure you are, and don't go 40 degrees off of horizontal. And then over here, are you going 30 degrees up? So again, I'm feeling spiffy because I made fancy polyline arrows at the end of my lines. And now I'm going to leave my free body diagram where it is so that I don't, so if I do mess something up, I still have my original to return to. And I am going to copy my 3 arrows, but not my dimensions. I don't want the dimensions, I just want my arrows. And I'll move a copy over here. Hello, I don't want a dimension. I want to delete that. Okay, so now this thing is 100 units long. Is that true? Let me type DI for distance. And from there to there, 100 things long, that's good. Okay, now I want to string these together tip to tail. Oh, looks like 2 of them are already tip to tail. This one is tail to tail, that's not good. So I will move this one. I'll grab it by the tail, that's my base point, and I'll move it down here, there. And now I can measure those distances. Let me undo that and show you something else first. I could also, what was I going to say? I could also, if I wanted to, do a different kind of tip to tail. I could move this tip to that tail and then move that tail to that tip. I'll still get the same answers. These guys are still at the same angles, and I'm still going to get the same lengths. I just did them in a different order. So I would now come in here and measure. That's 87.939 pounds. And this one is 65.27 pounds. I might go in here, if I'm going to leave my dimensions, I would go in here and add a pound sign, because we want to make sure we know what the units are. Okay, I think that takes care of that one. In the next short video, we'll come in and look at the third problem.